let's move to the next one presentation. It will be Gerson de Almeida will present it, and it is named Evaluation of a Beam Cloud Model using data from Chuva Project for Fortaleza, Ceará.
Hi, hello everybody. Well, I am Gerson Almeida. Sorry. Well, I am Gerson Almeida, and I'm presenting this work. Probably I was not best person to present it because I have not been deeply inserted in this work during its major development. But this work can be considered as a preliminary result from our project we are developing at Ceará State University, and also here at EAG at USP avec, with sorry, mixing with French, with Professor Morales, and we have as a motivation to develop a beam cloud model, a Brazilian beam cloud model, and the results I am presenting here were done because we need a problem during the development of a mix, the implementation, the mixed phase of this model. Are you hearing me well? Well, and because during the implementation mixed phase, we have a problem that described and the work that was the fact that the convection subroutine could not solve the convection if we were using a very large number of grid points. It means that's about 200 and 200 by 200 points convection using a resolution of 14 or 18 meters. And when you faced that problem, you needed to modify. One of the objectives of another objective of this work was find dynamical situation where mixed phase is very probable to occur. Well, this model is a beam model with two-dimensional cloud dynamic described on this work that I can show you later for who is interested. But basically, it is a wet, deep and free convection, and it conserves linear momentum, mass conservation, energy conservation, and water conservation based. The model has also a refined description and calculation of cloud microphysics that is based on nucleation, which was modified since the last version I presented on newspapers. Also, it is based on condensation, evaporation, collision and coalescence, collision and breakup that we also modified recently in spontaneous breakup. Well, those are the questions on which this equation on which it's based. And for doing those tests, we performed a series of simulations. Probably we had more than 300 hours of work on computers. And this model takes a lot of time because we use 100 beam classes to represent cloud drops. And cloud drops are considered ranging from 2 micrometers to 10 millimeters. The model will also use 168 beam classes to represent CCN, with which you can consider modification on chemical composition. And using this number of beam classes to represent CCN, we can evaluate nucleation, considering saturation varying from 0 at the cloud base up to 3% supersaturation. Well, the main work was based on and increase the number of grid points to 80, what means 6,400 meters to 230 to 230 grid points, up to 18 kilometers, with 800 meters resolution. Well, the data were taken from the project Chuva held in 2011 in March and April in Fortaleza, when we had some measurement points around the city, and at this site here in Inemet, there was radio soundings from where we take our initial conditions. Well, radio signals and all the data from Fortaleza were used. Here we have the kind of initial condition using on the model, and here we have the radio sounded that take all the points measured, and we use as control simulation. And here at the right we have a second kind of simulation based on the first one, where we proceed with smoothing those data observed on this profile. Well, we realized we performed a lot of a simulation and use both kinds of profiles. The model simulation uses a time step of 5 seconds for the dynamics, while you use 0.2 seconds for microphysics, and all clouds were simulated during 1 hour. Well, just a little detail, this model is for isolated clouds. Well, cloud condensation nuclei were considered for 3 regimes: maritime, pollutant, and intermediate, and all of them followed this kind of relationship relating the number of nucleated drops and the supersaturation. The values for C and K were those one for maritime, intermediate, and polluted. And considering that the profile, we evaluate if the model were able or not to produce rain, and you use those points, those stations here, to take data of precipitation, and we evaluated if our model could reproduce or not the precipitation measurement on those points. Well, here is some cases we simulated the temporal evolution of cloud water here in black and white, and the precipitation in colors for different situations represented for April 2011. And in all the cases we see the production of precipitation, but those clouds that go higher, they produce more precipitation as is expected. Probably that one that from the 9 April 2011 it has extended to higher levels, reaching the freezing level. Well, we have more cases shown here, and as you can see, this probably you cannot see because it's very small numbers here, but those clouds does not reach 4 kilometers high. Well, those are the results, and we have the modeled precipitation here. As you can see, all the accumulated precipitation are less than 2 millimeters, and in general they agree with the precipitation observed. Not for this case, as I told you, that probably the cloud has reached the freezing level or much above it. And those results are for profiles that have not been smoothed, while this one are for profiles that have been smoothed. Well, the conclusions is that this cloud model can represent the precipitation observed, but the fact is only 45% of the case when with the simulation of control are really reproduce the observed case. When we smooth the initial profile, this representation increased to 44% of observation. Well, another point of conclusion of this work is the fact that sometimes we have clouds that grow very high in the atmosphere, probably going at, let me say, 10 kilometers high, and produce a lot of ice and also increase the precipitation efficiency. So that's probably the fact that it's probably due to that this model cannot produce high precipitation rates like the one shown in the first case, like 38 millimeters accumulated in 1 hour. Well, that's all.
Thanks, Gerson, for your talk. Is any question for him? Henrique?
No, I use a 2D model. Yes, it's one of the stages of our work. When first have a model that can be used to be tested. So you need 2D dynamics, and we are planning in the next future, not in the very near future, to implement its 3D model, probably RAMS, which is a model that we know better than Wolf or something like that.
Please say that.
You are saying that you have used this model in cards. How that works?
Yes, in fact, we already developed the subroutine that calculates the charge transfer. You have to consider the fact that you have the mixed phase, have both super frozen droplets and the ice phase, and that they can collide between themselves. If you have those two phases, and you can calculate how the ice crystals can collide with other ice crystals, you can calculate, basically you can calculate the charge transfer between hydrogen. No, liquid water is not believed to have charge, but just the solid phase.
Use CCN for different scenarios. The results you showed is for clean, polluted, or
for clean.
Clean.
This is for clean. But you have done a lot of work with using different cloud microphysics. Basically, microphysics regimes. I mean, clean, intermediate, polluted. Basically, what happens is that if you have a more polluted environment, the model produces a little bit less rain by later in time. So it means that probably the cloud goes high, a little bit higher, depending on the dynamics you have in the environment. And depending on thermodynamics. Basically, thermodynamics defines how high the cloud goes. And the cloud microphysics says if it rains soon or later.
Yeah, the question is whether you would get higher cloud tops with polluted.
Yes.
Yeah, And then you would need the ice.
Yes, probably when you have a more polluted environment or environment with more cloud condensation nuclei, you have a cloud that goes higher. And in some cases, the warm phase does not produce enough rain as it does in the clean environment.
And the other question is whether the cloud tops you model are similar to the cloud tops seen by radar during that day, or not.
Well, we're trying also to develop some subroutine to see if the results from radar are the same using a clean environment to produce the cloud or not. But until the moment, what we have seen is that clean clouds have larger effective radius, so it seems that they reflect more the radar.
Yeah, but you have a cloud top from your simulation, right?
Right.
The question is, during that day, 9th of April, did you see cloud tops similar to those ones, or not?
That's we could not see yet the data radar. I've seen someone, but I don't remember which day was that, and I'm not sure which radar data I have seen, so I cannot answer you.
Okay, thanks, Gerson, for this presentation. And
Thank
then with his presentation, we will finish the numerical modeling session. Okay.